Hello everyone. Today, I will provide basic information about the shear safety of column beam connection regions. First through the 2018 Turkey Building Earthquake Regulation, then through the STA program. Before we start on this topic, there is an important concept we need to know. A concept is strong column weak beam rule. We need to know the strong column weak beam rule. Knowing this, we can understand the shear safety of the column beam connection region much more easily. It has been stated that in highly ductile systems, columns should always be stronger than beams, and design should be done accordingly. The fact that columns are stronger than beams means that beams will yield before columns. In other words, beams will have reached their maximum moment capacity and will have done so before the columns. While the columns continue to take the relevant moment, the beams reach a point where they no longer take any more moment, and in a way, plastic hinge formation occurs there. Beams can no longer take additional moment, while columns continue to take moment. Since columns are the structural elements that keep the building standing, it is very important for the columns to remain standing and still be able to carry moment. If the beams were stronger and the columns had yielded first, and if the columns were unable to carry the moment, then the structural system would have collapsed in a brittle manner. Because we want to design a highly ductile system, columns must always be stronger than beams. The shear safety of column beam connection regions is actually the term given to the control of the shear force value created by beams that have yielded, meaning beams that have taken their maximum moment on the column. So, here, for illustrative purposes, look, we have a symbolic moment pair shown here. The moment couple here actually shows the plastic hinge moment occurring in the beams. In other words, the beams have formed hinges. Our columns are still continuing to take the moment. A full strong column weak beam control has been achieved. It is the numerical value of the shear force acting on the columns at the exact moment when the beams take their maximum moment. More precisely, it is the control of this confined column control. In other words, the shear safety control of the column beam connection regions. Look, seen here, a moment couple is forming. We can express these moment pairs on the beams with forces. In this way, you can already see the forces. Here, this force exists within this beam, and it also exists within this beam. As seen, these forces create a shear force in our column. The shear force value occurring in this column beam connection region is calculated using the 7 to 11 equation. The formula is given here. According to this formula, the shear force generated here is calculated. Can the columns withstand this generated shear force? Can it withstand without any brittle fracture? This is very important, and the capacity of the column. If we have a confined connection, it's calculated with this formula. If it is an unconfined connection, the formula is being determined. The difference between these two formulas arises from the coefficients. Since more shear force can be carried in confined joints, our director has indicated this with coefficients and has taken the value of 1.7. That is assuming the values are the same. Assuming we are speaking hypothetically, in a confined joint, 1.7 times more shear force can be carried compared to an unconfined joint. So what does an unconfined joint mean in a confined joint? Let's explain this. As seen here, a confined joint means that all four sides of the relevant column are surrounded by beams. This is a condition. Another condition is that the beams connected to the columns must be at least 3/4 of the column size in both directions. In other words, the width of our beam here is B1. the value of our column here is B. Our column is of width B. B1 here, and B2 opposite it, are at least 3/4 of the B value of our column. This is of course valid in both directions. Same applies to B3, B4 where the H value is 3/43. It needs to be at least 3/4 of the column size when this condition is met and all four sides are surrounded. Refer to it as a confined joint. Other types of joints that do not meet these conditions, that is, those outside of this control, or outside of this confined joint, are referred to as unconfined joints. This is very important. If we examine the formulation of the shear force value occurring in the column, the formula is calculated as follows, since the reinforcements in the beam here have reached yield. Characteristic yield strength value is used. It is multiplied by the total area of the reinforcements in the beam, and then this value is multiplied by 1.25. In this way, our shear force value in the column is calculated as a general principle. So how are AS1, AS2, that is these reinforcement areas, calculated? They are calculated as follows. Now, value as 1 represents the total tensile reinforcement formed at the top under negative moment for this left input. Similarly, for the adjacent entry, the AS2 value shows the amount of reinforcement placed in response to the tensile force that occurs at the bottom under positive moment. And since both create shear force, the formula is calculated as their total. However, it is necessary to consider both types of calculations here. The moments here can also come in the opposite direction. Therefore, for that reason, the amount of reinforcement at the bottom of the left beam and the amount of reinforcement at the top of the right beam may be required in the calculations. Their total is also considered, whichever is the largest, and in whichever case the largest reinforcement area occurs. That is taken into account, and the value E, which is our shear force value in the column, is calculated. In this regard, the calculation of the hand is also very important. Here, one of the most important factors is the calculation of the strength amount in our column is considered as 1.7 if it is a confined joint. If it is unconfined, a value of 1 is considered. So when we look at the content of this formulation, what is considered when calculating the shear force that the column can carry? First of all, the FCK value is very important. That is, square root of the FCK value is taken. The FCK value refers to the characteristic compressive strength of the column. This is important. So, effective area of the column is very important. What we call the effective area is the value of BC times H. In other words, the H value. One dimension of our column was already H. Dimensions of our column are defined as B and H. Here, the value of B. D is very important. Important. Why is it important? Because by adjusting the BC value, we can increase the amount of shear force it can carry. If the BC increases, the transferable shear force value increases. Therefore, the higher we can keep the BC value, the more comfortable we will be in this control. How is the BC value calculated? The effective shear area is the BC value multiplied by the H value, and I can show how the BC value is calculated in more detail as follows. If the beam width is smaller than the column width, for example, if the B1 and B2 values are indeed smaller than the B value, the position where B1 and B2 are connected to the column is very important. For example, let's consider B1. B1 is connected to the column at the exact midpoint. That means it is connected exactly in the middle of B. So, the distance to the left edge of the column is the B1 value. B2, B2. And let's say the width of our entrance is BV1. Now, how is the effective BC value calculated in this situation? Whichever of our B1 or B2 values here is smaller. In the example I mentioned, they are equal because I provided it from the exact center. Whichever is smaller is taken into account the value there is considered. If B1 is smaller, B1 is taken into account. If B2 is smaller, B2 is taken into account. And twice the relevant value is considered. This becomes our BC value, because it may not always act from the center. In other words, it may act closer to any edge. So, the important point here is the position where the beam is connected to the column. In other words, wherever the beam is connected to the column, the distance from that connection point to both edges of the column is calculated. Here, these values are represented by B1 and B2. The smaller of these values is considered. Whichever is smaller, B1 or B2, twice that value is taken. This is how the BC calculation is done. Therefore, the more we shift the beam towards the center, the larger our BC value will be, because the more we place it towards the edge. For example, if we place it close to the left edge, the B2 value will increase, but since B1 will decrease and the minimum value is considered, the B1 value will be taken into account and twice the B1 value will be used. Therefore, if we place it exactly in the center, we will obtain the maximum BC. That will be equal to the column zone B. This is because B1 and B2 will be equal to B divided by 2. Twice that value will be equal to B. This is how the BC values are calculated. By adjusting the position of the beam on the column, we can increase the shear force value that the column can handle. And this is a very important point, because without changing the size of any column, without changing the size of the beam, or without making any modifications to any reinforcement, we can increase the shear force value that can be obtained by simply adjusting the position of the beam. This allows us to achieve this control. Apart from that, if our beam widths are not as shown here, but are equal from column to column, or larger than the column, then the beam widths are taken as the width of the column. In this case, if the BV1 and BV2 values are equal to or greater than the B value of the column, then the BC value is taken as the width of our column. In any case, in other words, it is taken as B. This is very important. Also, the BC value must never, ever be smaller than BV1 here, provided that BV2 is smaller. If BV2 is smaller, then BV2 is taken into account. I am talking about the formula here. The BC value can never be greater than the sum of the column's other dimensions with the H dimension, considering the smaller of the BV values here. The BC value must always be smaller than this value. Here, it is stated as BV1. This is written considering that BV1 is smaller than BV2. If BV2 is smaller, the formulation here is adjusted as BV2 plus H. The other BC is important in this regard and is calculated in this way. Additionally, the amount of reinforcement in the beam can be reduced to ensure this control. When this amount of reinforcement is reduced, the shear force value created by the beam and the column will decrease. Here, AS1 and AS2 can be adjusted to reduce the amount of reinforcement in the beam. The load on the beam needs to be decreased. If too much load is applied to the beam, you need to reduce it. You have a rib slab You can change the direction of the ribs. Less load can be transferred to the related beam from there. In this way, if the amount of reinforcement here decreases, the shear force value in the column will also decrease. Apart from that, why is this check considered in highly ductile structures? I would also like to provide information related to that. The main reason for examining this control in highly ductile structures is to avoid brittle failures. As I mentioned at the beginning of the video, because we are designing a continuous structure, we never want brittle failure, and brittle failure is occurring here. Therefore, this is considered in high continuous systems. However, in mixed structures, limited continuous structures, this check is not required. There is no need to look at this check. So why is it not necessary? Because an excessive amount of shear walls are used in structural systems with mixed ductility levels and in structural systems with limited ductility levels. The shear wall ratio, that is, the ratio of the moment taken by the shear walls, should be above 75%. As specified by our regulations, this is how they are designed. There are too many shear walls in the structure. Because there are so many shear walls and they are the structural elements that work the most during an earthquake. They absorb a large portion of the earthquake's load. Since they absorb the loads themselves, no extra load is applied to the beams. Due to any earthquake as a result, not much moment is generated in the beams. The AS1 and AS2 values here are much smaller. Therefore, there is no need to perform this check. This is because the shear force value created by the beam in the column is very low. Therefore, this check is not necessary in normal frame systems or high ductility systems. Under the effects of the earthquake, columns and beams can experience significant shear force values and high reinforcement areas due to the absence or scarcity of shear walls in the structure. For this reason, checks are required in high ductility systems. This is a very important point if your structure has a large number of earthquake shear walls. You do not need to perform this check. In other words, if you are not designing a highly ductile system, this check is not necessary. And the beams are designed under vertical loads, meaning the reinforcement is also done under vertical loads. There is one more point I would like to mention in the relevant regulation articles. Yes, the minimum transverse reinforcement conditions are important here in the column and beam joint region. If the relevant articles are examined, as seen, there is a different rule for confined joints and a different rule for unconfined joints. Now, if the joint is confined, at least 40% of the transverse reinforcement amount calculated for the plastic hinge region of the lower column must also be used throughout the joint region. And the transverse reinforcement diameter should not be less than 8 millimeters, and its spacing should not exceed 15 centimeters. If it is an unconfined joint, then at least 60% of the transverse reinforcement calculated for the lower column's critical region is used along the joint region to stay on the safer side, as unconfined joints are more dangerous. And here, the transverse reinforcement diameter should not be taken as less than 8 millimeters. That is, our stirrup diameter is our transverse reinforcement diameter. And the transverse reinforcement spacing here should not exceed 10 centimeters. So, while it is 15 centimeters above, there is even stricter control here. The spacing should not exceed 10 centimeters. We can show its shape here in a healthier way. We can also view this through the picture. If we refer to figure 7.3, I am going up a bit. Yes. Look at the figure here. As seen here, there is a column confinement region, and this confinement region continues in the joint region here. As stated here, the transverse reinforcement calculated for the lower confinement region along the height of the lowest beam, that is, at least 60% of the transverse reinforcement in the column confinement region here, is placed here. Since this is a confined joint, it is specified that the reinforcement should be placed at 10 centimeters intervals. So, the confinement region here also extends to the joint part. This is what is meant here. Other than that, if we come to the STA program, when we get to the handbook training section, in the STA program, we come to the frequently asked questions. And here, when we click on the third option, yes, look here. It explains in more detail how we can increase the effective width, or rather the effective area, of BJ, which is the B times H area, both in the program and, more precisely, in the regulations. First, look here. We have a beam with a width of BV, and a column with a height of HC, and the beam's width BV is the same as the column's width B. We are currently facing a situation where there is a deficiency. Of course, to address this inadequacy, we can shift the column here, etc. We talked about these. These are the most effective ways, but increasing the cross-section is also an option. There might be a possibility to increase the cross-section here as well. For example, when you look here, HDL has increased. In this way, the effective area has been expanded. The size of the column has been changed. For example, this was done in the last option. This could be possible. Or the size of the beam can be changed, as mentioned. Or the most logical solution might be to change the position of the beam by simply changing its position without making any dimensional changes or incurring extra costs. The effective value B can be increased here. This is important. The most logical way here is this, but of course, depending on the situation. For example, if we encounter this error in a few columns, we can solve this problem with reinforcement modifications, or we can solve it with the effective shift here. But if there are too many elements, and if we can't reach a solution by shifting the beam and increasing the effective area, then of course we will need to increase our cross-sections, or we will need to improve the quality of the concrete in the structure. Or we will increase the ratio of shear walls in the structure. We will reduce the effects on the beams there to some extent. So there can be solutions in this way. Now I will provide information on how this check is performed in the program and where the analysis result is obtained from, using an example. Before moving on to the relevant example, there is one more thing I would like to mention. As seen here, the beam has been shifted. This was at the very corner on the column. It was moved more towards the center. We call this method dance. This is also how our director does it. It's the same in the Eurocode, so this is a sound method according to the Eurocode as well. However, the Eurocode performs a more rational calculation. I can explain the reason for this as follows. Look, this calculation here actually belongs to the Eurocode. A calculation from the Eurocode defines the breaking line as half of the Hess value, which is the height of the column within which the beam remains, meaning the Hess section is divided into two equal parts. It takes this and uses it in the effective area. In other words, the values indicated here as B1 are actually the Haas/2 values in the Eurocode. So it is half the height of the stirrup here, and when we connect the beam to the column in the middle, we take the distance from this connection point to the edge of the column and multiply it by 2. In other words, when we connect it exactly in the middle, it equals the width of the column. Here, for example, you connect the beam you take the width of the beam. At the same time, you take the h divided by 2 part from the fracture line here, and add the parts indicated by BB1, and the B value increases significantly. As a result of this increase, our column becomes capable of carrying more shear force. Yes, now if we examine this topic with an example. Yes, here we have a sample structure. We analyzed this structure, and as a result of the analysis, problem of a confined column arises. In the column seen here, in other words, the column beam joint safety does not meet the shear control requirements. Can also view this here when we click on it. It is also written here. This condition is not met, and the detailed calculation of this is provided within the program. We can view the detailed calculation here. When we click on this option, it shows us the detailed calculation. As seen in the figure, our relevant column is surrounded by beams on 3 sides, not 4. And because it is surrounded on 3 sides, it is referred to as an unconfined joint. Calculations here are made by taking the other coefficient as 1, and it has been calculated accordingly here. Using the formulation shown in the relevant code with respect to reinforcement areas, the shear force value is calculated, and the force that the column can bear is also calculated. Using a formula here, it is calculated as being at the top of a floor number, meaning it pertains to an unconfined joint. The values are shown here. Look, while the value that the column can bear is 42. Shear force value on the column is 59. And therefore, its control is not met. This is, of course, done for the x direction. As you can see, it is already written here. And it is done in the same way for the y direction, and the control is also not met in the y direction. In the y direction, it is not met by a small margin. Look here. The program also provides detailed calculations for the beams. It takes into account the beams in the x direction. It considers the beam in the y direction and calculates the effects related to it. Look, the BCBHC values are written here. Here are as 1 plus as 2 values as well. As I mentioned, in the regulations here, program considers the maximum value. And look, in the x direction it came out as 9.5 to 11.7. They considered 11.7. Here, they considered 8.5 in the y direction, in square centimeters, and they performed the calculations accordingly, and it does not meet the requirements. Here, they offer a suggestion. If you cannot perform section enlargement here, you can increase your shear wall ratio, or if you also improve the concrete quality, the FCK value here will increase. Or, if possible, the positions of the beams here can of course be adjusted. Alternatively, a solution can be made with reinforcement. For example, in this project, only this element, the 210 column, has this issue. Therefore, specifically for this column, for example, the reinforcement areas of the beam connected to the column can be changed in both directions. A simpler reinforcement distribution can be achieved. We can change it like this. Here, we can come over the relevant element and modify the reinforcements, the beams. Yes, here. We can arrange the reinforcements of the beams to meet the necessary areas. And if possible, we can reduce the amount of reinforcement slightly. The column size has been made at the minimum limit of 30 by 30. We can enlarge the column size a bit. Alternatively, the column confinement control in the y direction is not achieved by a very small amount. Here, instead of connecting it from the edge, we might have the chance to connect it more centrally for better effectiveness. We can connect it that way and then check the results again. This is also an important option in terms of applicability. Yes. Now I have increased our column dimensions to 30 by 30, and 35 by 35. Here, I have adjusted the beam on top to have the maximum width on the column. I have set the eccentricity accordingly. And we check here. We can see that it has a positive effect in the Y direction. Look, we can actually see that the necessary condition is met, albeit with small differences in the Y direction. It wasn't meeting the requirements earlier, but increasing the size of the column helped us in this matter. Similarly, of course, I tried to place the beam closer to the middle regions of the column to meet this requirement, and in this way, we achieved it in the Y direction. Of course, it is still not sufficient in the X direction to ensure this in the X direction. Column size might need to be increased a bit more. Alternatively, reinforcements can be adjusted as I showed earlier, or the beam dimensions can be slightly enlarged. In this way, control of the column has been ensured. However, with this small change we have eliminated the problem in the publication. Yes, that's all I have to say on this topic. Thank you very much for listening to me. I wish everyone good work.